Okay, we are going to work on this in terms of sheet, and this is part 1. 2 isotopes. What's isotopes again? So every time you see a word, you should be thinking about the definition. The isotope means it is the same element. So what does that mean? Same number protons, but it has a different number of neutrons. Okay. So we have 2 isotopes of potassium listed below. In terms of subatomic particles, state one similarity between potassium-37 and potassium-42. So in terms of subatomic particles, my answer must reference subatomic particles. So those options are proton, neutron, electron. So one similarity between them. Well, notice these mass numbers are on top, but there's no atomic number on the bottom. Where would I find that atomic number? Well, I would go to the periodic table and I would look for K. And you see it says 19. It doesn't say it's 19 only if it's one version of potassium. If it has a K as a symbol, if it is potassium, it has 19 protons, period. Its atomic number is 19. So the number below for both of those would be 19. So one similarity, they both have 19 protons. In terms of subatomic particles, so again, my answer must reference subatomic particles, and I have 3 options. State one difference between them. I don't have to give it in specific terms of numbers, so I will say they have different numbers of neutrons. That's a difference, right? In terms of half-life, how are K37 and K42 different? Well, this is a reference table question. So I need to go to table N. And oh, look, here they both are. K37's half-life is 1.23 seconds. K42's half-life is 12.36 hours. Okay? So how are they different? Okay, K42 has a half-life in hours, while K37 has a much shorter half-life, only in seconds. I probably don't even need that part, but I'm going to be extra specific. All right, let's look at the next one. Look at this equation. In terms of the collision theory, so as soon as it says this, my answer must talk about collisions. Why adding extra N2 produces more NH3? More NH3 is produced because there are more collisions. We get more product when there are more collisions. In terms of what specific kind of collisions, it's effective, so more effective collisions. In terms of Le Chatelier's principle, all right, when they say this, all you need to say is you have to talk about shifting the equilibrium. So in terms of Le Chatelier's principle, state why adding extra N2 produces more NH3. So when I add N2, the equilibrium shifts to the right, which uses up this extra N2, but also uses up some H2. And then here's the arrow. So on the other side, it's going to increase the amount of NH3 and also increase heat. So the equilibrium shifts to the right when more N2 is added. In terms of ground state and excited state, so guess what my answer has to mention? Those two things. Explain how a bright line spectrum is produced. Electrons that fall from excited state to ground state produce the bright line spectrum. They release energy as light. Okay. All right, so let's look at this data table. State in terms of intermolecular forces. So I have to talk about intermolecular forces. Why the boiling point of propane at 1 atmosphere, notice that's in the table right here, is lower than the boiling point of butane. So you can see propane is 231 and butane is 273. So why is the boiling point lower? Butane has stronger intermolecular forces. So its boiling point is higher. Okay, you could have reversed it and said propane has weaker intermolecular forces, so its boiling point, I forgot the word point, is lower. Okay. In terms of valence electrons, why is Li more like Fr than Be? So my answer has to talk about valence electrons. Now, can you guess what I need to look at here? If you were thinking the periodic table, you would be right. So I'm going to find these three elements. Li, valence electrons, 1. Fr, valence electrons, 1. And also, what was the other one? Be. Be, valence electrons, 2. So, why is Li more like Fr? Both Li and Fr have 1 valence electron. When NaCl is dissolved in water, the temperature of the solution decreases. Explain this statement in terms of average kinetic energy. What does this mean? Average kinetic energy is literally the definition of temperature. So, if temperature decreases, the average kinetic energy also decreases. Because literally, temperature is a measure of average kinetic energy. All right, NaCl has a higher melting point than C6H12O6. Explain this in terms of bonding. Okay, so NaCl has ionic bonding, so its boiling point with melting point. So it's, well, actually both, but this question said melting point. Its melting point is higher. C6H12O6 has covalent bonding, so its melting point would be lower. Explain this statement in terms of intermolecular forces. So C6H12O6 has weaker intermolecular forces, so its melting point is lower. Its boiling point is also, for that matter. Okay? All right. In terms of valence electrons, explain why copper is a conductor. So I have to talk about valence electrons, and I have to talk about copper and conductor, kind of. So here's copper right? Copper has one valence electron, but that doesn't really explain why it's a conductor, okay? So copper is a metal. So its one valence electron is in a mobile sea of electrons, and this makes it a conductor. Okay. All right, let's see. In terms of location on the periodic table, so we got to talk about where it is on the periodic table. Explain why copper is a conductor. Well, let's just look real quick. Copper is in the middle in this transition metals. It's also to the left of the staircase, so it makes it a metal. So copper is on the left side of the periodic table. So it's a metal and a conductor. Alright, CH4 will not dissolve in water, but NH3 will dissolve in water. Explain the solubility in terms of molecular polarity. Okay, so I have to include both. Alright, so water and NH3. So water is polar. NH3 is also polar. Therefore, NH3 will dissolve in water. Remember, like dissolves like. Anything that is polar and also anything that is ionic will dissolve in water. If it's nonpolar, it won't dissolve in water. Okay. Chemical X has a boiling point of 75 degrees Celsius and chemical Y has a boiling point of 126 degrees Celsius. Explain this difference in boiling points in terms of intermolecular forces. So I have to talk about intermolecular forces. Okay, so X has the lower boiling point, right? So X has weaker intermolecular forces. So its boiling point is lower. All right, let's look at this one in terms of heats of vaporization. So what does that mean? Heat of vaporization, okay, is when we have a heating curve, right, like this. Oops, not this. Okay, so here we have melting, that's heat of fusion. Here we have vaporizing, we have boiling, so there's our heat of vaporization. So if something has stronger intermolecular forces, it's going to take more energy to make it melt or more energy to make it boil. So since X has a lower boiling point, it would have a lower heat of vaporization. It would take less heat to break those bonds. So X would have a lower heat of vaporization. All right. Here we go. Look at this one. Using the symbol, so basically a circle representing a particle of substance X, complete the diagrams. Include at least 6 particles. So for a solid, right, they're packed tightly like this. For a liquid, the particles are still going to be found at the bottom, but we're going to have more space in between them. Again, I drew more than 6. You had to have at least 6. Gas, they're really spread far apart. That's where I just have to be careful with drawing 6, right? Explain the differences in particles from A to B in terms of energy. Okay, well, let's talk about kinetic energy. Kinetic energy is stored energy, and when we're looking at a heating curve, for example, the lowest potential and the lowest kinetic energy are going to be down here as just a solid. So particles in B have more energy, more kinetic and more potential energy. Explain the change from A to B in terms of particle arrangement. Well, here in A, it's very ordered, in which has low entropy. Remember, entropy means disorder. In B, we're starting to get more spread apart. So in terms of particle arrangement, the particles in A are very ordered and have low entropy, entropy being disorder. Explain the difference between A and B in terms of intermolecular forces. Well, if we have a solid, those particles are very close together and their intermolecular forces are very strong. So particles in A have strong intermolecular, we'll say stronger intermolecular forces. Okay. All right, now for this one, part of it is a little bit cut off in this diagram, so we have to, the one that I print for you will be better. It says, explain in terms of heat of fusion and heat of vaporization why the heat added during interval DE is greater than the heat added during interval BC. So let me just real quick sketch what this does look like, just so you can see what I'm talking about. Okay, so this is A, B, C, D, E, F. So you can see in this graph, which once I print this correctly, you'll see that the line for BC is shorter than the line for DE. That means the heat of fusion is less than the heat of vaporization. Okay, so explain in terms of the heat of fusion and heat of vaporization why the heat is less. So there is less heat in BC because, and we have to say heat of fusion and heat of vaporization, because the heat of fusion is less than the heat of vaporization. And there we go. We finished the first set of in terms of questions.